Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020, and this is the conclusion of the lecture entitled Solving Non-Homogeneous Systems of First Order. By way of introduction, matrices can be used in an entirely different manner to solve a system of linear first-order differential equations. Recall that the simple linear first-order differential equation x prime equal ax, where a is a constant, has a general solution x is equal to a constant c times e to the at, and c is a constant. It seems natural to ask whether we can define a matrix exponential function e to the at, where a is a matrix of constants, so that the solution of the linear system x prime equal a x is equal to e to the at. Well, we now are going to talk about that it is possible to define this exponential function so that this is a solution to the homogeneous equation x prime. Now this is e to the at times c. Now a is an n by n matrix of constants and c is an n by 1 column matrix of constants. Note in one that the matrix c post multiplies because we want that to be an n by n matrix. That's a fact of matrix computations. Okay, so here is one way to consider defining it, and that is motivated by the Maclaurin series for e to the at, and this is what we get for that. And we know that this series up here converges for all t. So if we use this series with 1 replaced by the identity matrix and the constant a replaced by the n by n matrix A of constants, this is a definition that we can have. And it can be shown that this converges to an n by n matrix for every value. What's really happening is those factorials grow really fast, and so that goes to 0. And when I multiply like a squared is going to be a times a cubed is going to be a times a squared, and so on. Okay, so here's an example. You want to compute e to the at for this matrix. You know what to do. Let's see how you did. Well, when you start doing powers of a here, what you find out is, since this is a diagonal matrix, you're just getting the powers of the diagonal elements. And so we have that. So now when we use the definition, we will put these being the coefficients as we go along, and we're multiplying by t. But you see the only time you're going to be non-zero is along the diagonal, and so you'll get this infinite series here and this infinite series here, and so that means that e to the at in this case is e to the 2t in that position, it's e to the 3t in the other position, and it's 0 otherwise. Now this will happen anytime you start with a diagonal matrix where you have only non-zero elements on the diagonal. Then e to the at is just going to be given by this equation. We can also take the derivative of the e to the at, and the derivative, doing term by term here, is the derivative of a constant vector is just is a constant. So we go through, we take the derivatives here with respect to t, and we'll get this. But then I can factor the a out, and note that this is e to the at yet again. So you see the derivative of e to the at, where a is a matrix, is the matrix A times e to the at. Now we're going to show then that this means that the equation that we had, this matrix exponential, is going to be a solution to this. And in fact, here's the equation 1 that we were talking about, that this is a solution for every n by 1 vector c of constants. So what I'm going to do is I'm going to take this and just plug it into the equation. So if I take the derivative of that with respect to t, I get a, and this is e to the at, and the constant just sits there, will be a post multiplication kind of thing, and that's the same thing as a, it's associative, and so I will do this, and that's a times x. So you see this e to the at times c, where those are constant vectors, n by 1 constant vector, is a solution to this differential equation. And moreover, so they're solutions, but since the determinant of this at 0 does not equal 0, that we can conclude that this is a fundamental matrix of this system. So it is linearly independent. We can apply this to non-homogeneous systems as well, because in the same way that we solved this non-homogeneous equation to get this, if we have this non-homogeneous matrix equation, we can get this by analogy. And notice the c has to be post-multiplied here, but otherwise we have that. And since the matrix exponential e to the at is a fundamental matrix, it's always non-singular, and in fact it can be shown that e to the minus as is the inverse of e to the as, the matrix inverse. So in practice this can be obtained just by replacing t by minus s, and you could do that integral, or at least you could attempt to do that integral. Now, the definition of e to the at given can always be used. This is the first definition to compute it, but the practical utility is limited because it's a power series, it's an infinite series. So we often try to find other ways to compute it, and here is one way you can also compute it. So let's use the Laplace transform to find out a different way to define e to the at. Okay, so we saw previously that x equal e to the at is a solution to this differential equation. And since e to the a0 is I, x equal e to the at is a solution of this differential equation. So what we're going to do is take Laplace transforms of this entire thing, as we've done before. So x s, that's in a transform, is the Laplace transform of xt, and that's the Laplace transform of e to the at, because that was the solution to the initial value problem. So then the Laplace transform of this entire thing is going to be s x of s minus capital X at 0, that matrix, equals, and this is a x s. Or, rewriting this, that this is equal to the identity, because what you see, we can move this over to the other side, we can solve that. So this is equal to the identity. Now, what we can do now is we can take and multiply by the inverse, and it's not really multiplying, it's operating by the inverse, but we're multiplying, I guess, the matrices, so the inverse on both sides. So that means that when we multiply this side by the inverse, we just get x of s. When we multiply the identity times the inverse, we get si minus a inverse. Now, what that meant was that xs is equal to this, so that means that the Laplace transform of e to the at is that inverse, or e to the at is the inverse Laplace transform of that. Why don't you use that definition and see how you go here. So use the Laplace transform to compute e to the at for a being this. You know what to do. Let's see how you did. Okay, so first thing we need to do is compute this si minus a. That's what we get when we calculate that. And we have to invert that matrix, and when there's a calculation involved, when we invert the matrix, we will get this, and we'll do partial fractions on each of those entries, and then we will invert these using the inverse Laplace transforms, and that is our result. In closing, Now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.